let's talk about one of the most maddening problems in the data world. You've got a query, it's on a massive table, it's critical, and it's just so slow. Today, we're putting on our data doctor hats to figure out why.
We've all been there, right? You have this billion-row table, a dashboard everyone is waiting for, and your query feels like it's crawling. And you're on Snowflake. It's supposed to be fast. So what's really happening under the hood? Well, let's find out.
So, our journey starts with this one big question. How in the world do we speed up a query that's running against a giant data set?
Okay, first things first. When it comes to performance tuning, you have to stop guessing. Just randomly making your warehouse bigger or tweaking your SQL without a plan, that's like throwing darts in the dark. To actually solve the problem, we need evidence. We need to diagnose it properly.
And our go-to diagnostic tool is the Snowflake Query Profile. Honestly, the best way to think about it is like an MRI for your query. It gives you this incredible step-by-step map of everything Snowflake is doing, and it shines a big bright light on exactly where the bottleneck is. This is always where you start. All right, so now that we have our MRI machine, let's go on the hunt for the usual suspects that cause these slowdowns. You know, after you've looked at enough of these query profiles, you start to see the same villains show up again and again. I like to call them the 4 horsemen of poor performance, and they're the classic symptoms you're looking for.
Horseman number 1 is excessive scan. Just look at this donut chart. To get the data it needed, Snowflake had to read 95% of the entire table. That's crazy inefficient. It's a dead giveaway that your data isn't organized in a way that helps answer your question quickly.
Then you've got horseman number 2, the exploding join. This one is brutal. You join a couple of pretty normal-sized tables, maybe 1.5 million rows and 6 million rows, and suddenly, boom. The result is over 100 million rows. That explosion creates this massive data tsunami that just clogs up everything downstream.
Our third horseman is remote spillage. If you ever see this message in your query profile, it's bad news. It means your warehouse completely ran out of memory and had to start writing temporary data to remote storage, which is way slower. Performance basically just hits a brick wall. And last but not least, we have queuing. Now, this one's a bit different. Your query might actually be perfectly written, but it doesn't matter because it's stuck in traffic. The warehouse is totally swamped with other jobs, so your query is just sitting there, waiting in line, not even getting a chance to run.
So we've seen all the symptoms, right? But what's the underlying disease causing all this pain? Well, that brings us to what I call the real-time trap. See, most of the time, those 4 horsemen, they're just symptoms. They're not the real problem. The true root cause is often a deep architectural flaw, a very common design choice known as the nested view anti-pattern. So why are nested views so bad? Well, remember, a view isn't stored data. It's just a saved query. When you build a view on top of another view, which itself is built on another view, it's like having a recipe that tells you to go look at another recipe, which then points you to a third recipe. By the end, you hand this tangled nest to Snowflake's optimizer, and it just gets totally confused and spits out a horrible, inefficient plan. Okay, we've properly diagnosed the problem. Now, let's talk about the cure. We need to ditch this broken pattern and move to the gold standard solution. Now, your first instinct might be to just use a materialized view. And that's a good thought, but there's a huge catch. As the official Snowflake docs point out, a materialized view can't do joins. It can only work on one single table. For our complex problem with multiple joints, that makes it a non-starter. So this means we need a fundamental shift in our thinking. We have to stop trying to calculate everything on the fly, in real time. Instead, we need to prepare the results ahead of time. Think of it this way. You wouldn't bake a cake from scratch every single time a customer wants a slice. No, you'd have cakes already baked and ready to go. And this table right here really says it all. A standard view? Yeah, it's flexible, but it's slow. A materialized view is fast, but it can't handle joins, so it's out. But creating a materialized table, that's the gold standard. It gives us the best of both worlds, all the flexibility we need for complex logic and joins, plus absolutely blazing fast performance. We've got our prescription now. materialize the logic into a table. But for long-term HERF, we have one more crucial step. We have to build a faster foundation for our new table. And that's where clustering comes in. The library analogy is perfect here. Imagine getting new books and just randomly throwing them on shelves. It'd be impossible to find anything. Instead, you organize them by genre. Clustering does that for your data. It physically groups related data together so Snowflake doesn't have to hunt for it. The difference this makes is just staggering. On the left, with an unclustered table, Snowflake has to scan all 10 terabytes to find what it's looking for. But on the right, with a properly clustered table, it only has to touch the 100 gigs it actually needs. That's a potential 100x speed up. This directly kills that excessive scan horseman we saw earlier. So let's just wrap this all up. It's a clear, systematic process. You start with the symptom, a painfully slow query. You diagnose it with a query profile, looking for those 4 horsemen. You find the root cause, which is often that nested view anti-pattern. The prescription? Materialize all that logic into a real physical table. And the foundation for long-term speed? You cluster that new table. And that leaves us with one final, very important question to ask about our own work. Views are tempting. They can make things look neat and tidy. But is your data architecture actually designed for performance? Or is it just designed to look good on the surface? Thanks for joining this explainer.